Let me just introduce this tutorial. The title is High Performance Network Programming in Java. Some familiar names from our last presentation, which is fantastic. So this is led by Dinesh Kumar, Kshitij Doshi. My apologies for probably mispronouncing that.
You got it right.
Rodolfo de Vega, and again, Harshad Sane. Let me, so I think I see some new names, I believe. So let me do a quick introduction. Just reading the bios for this excellent team. Everyone's from Intel. So Dinesh Kumar is a network software engineer in the networking and edge group at Intel, working on Ethernet product development and programmable network solutions, as well as network technologies, enablement, and optimizations for cloud and data center applications. He joined Intel in 1999 after completing his MS in computer science from IET University, India. Harshad is a performance engineer in the data center and AI group with a deep technical expertise in system software, memory, and CPU architectures. He specializes in performance monitoring, software optimization, and tool development with focus in the cloud domain. Harshad joined Intel as a college graduate in 2008 after completing his MS in electrical and computer engineering from UC Boulder. Rodolfo is a cloud software engineer in the data center and AI group, supporting customers and cloud service providers in optimizing their workloads for performance, both on-premises and in the public cloud. He joined Intel in 2000 after completing his BS in computer science from St. Martin's University. Last but not least, Doshi works at Intel Corporation in the data center and AI group, where he focuses on performance optimization of workloads and cloud instances. He obtained his undergraduate degree in electrical engineering from IIT Mumbai and his MS and PhD degrees in electrical and computer engineering from Rice University. His research interests span distributed systems, memory, and storage architectures, and resource management. So, with that, please take it away, guys. And maybe I'll just say, please post your questions. A lot of them are coming into Zoom chat, which is fine, but I think it's best if we put them into the Slack channel, if you're on Slack, in the channel named with the same name as the talk, High Performance Network Programming in Java. Yeah, and with that, please take it away.
Thank you, David. And hi, I'm Doshi. Together with Dinesh, Rodolfo, and Harshad, we're delighted to bring you this tutorial on high performance network programming in Java. So what's the rationale for this tutorial? Traditionally, the model for performing I/O is synchronous, or where when an application performs I/O, it typically the software threads that are performing the I/O wait until the bytes have been transferred to or from a device. Now, this is a very simple model for programmers. It's very easy to get it right, but it also creates various performance challenges, as we will soon see. And what this tutorial will be about is describing a very mature non-blocking framework for performing networking I/O. And also, as part of this tutorial, we are also including technologies that go beyond Java and achieve additional efficiencies for the performance-conscious programmer. So with that, let me go to the next slide. So I/O is a very natural part of computing for many applications. And typically what happens is that when software threads are referring to data in memory or in processor caches, they're largely performing non-blocking memory accesses, in the sense that these are accesses for which the processor will find something else to do while one part of the processor is waiting for the requested data to arrive. Depending upon where the data is going to come from the cache hierarchy or from memory, that can take anywhere from a few nanoseconds to tens of nanoseconds, sometimes hundreds. But there is sufficient instruction level parallelism for the CPUs to mask most of those latencies. But when I/O is performed between memory and storage and network devices, typically these are interactions that can range anywhere from tens of microseconds to tens of milliseconds. And so there's just not enough way to cover those kinds of latencies with the running software thread. So typically the threads will yield, and they will later on get completion status, get interrupted, whatever, and continue. Effectively, the view from the programmer's standpoint is performing various compute operations, performing some kind of an I/O operation that might require blocking. That blocking occurs completely transparently to the programmer, and then when that I/O completes, the computation proceeds forward. So the programmer has a very simplified view, and in that simplified view, that means in any I/O errors or exceptions that happen are naturally handled in context, because the total state of the system at that point is known to the programmer. Now, one of the problems with waiting for I/O completions in this way is that it's wasteful. Why is that the case? Well, today we have many different network and storage devices that perform at very high throughput, albeit at modestly reduced latencies. So what tends to happen then is you end up having to block a significantly large number of threads that may be waiting for those I/Os. At the same time, we have many CPUs to keep busy. So effectively, what ends up happening is we burn up a lot of thread memory, stack memory, and so on in order to wait for I/Os. There are also the overheads associated with context switching and very low CPU cache hit rates when this kind of switching becomes very frequent. But there's also a practical problem. For many applications to really mask I/O latencies, they have to have sufficient amount of application level parallelism, sufficient amount of thread level parallelism, and that's not always easy to architect. It depends a lot on different applications. So the natural cure for this is to have I/O reactive programming patterns where computations are kind of blocked up as chunks of computations that can be given to the same thread or the same groups of threads, and kind of a division of labor. One set of threads goes through and handles all of these computations in turn, and as the need arises for I/Os to be issued, those might be performed by an application's async I/O calls. And when those I/Os complete, then various types of primitives, whether it's through callbacks, completions, futures, promises, etc., you end up moving the computational graph forward in the logically synchronous fashion by updating state, by signaling or assuming something else. Sometimes it's done by support in languages, and sometimes it's done explicitly through support in algorithms. So this is the kind of pattern, right, where you're reacting to the completions of these I/Os. Now, performing I/O asynchronously while dependent tasks are activated as callbacks is a very high performance software programming model, but writing such I/O reactive code from scratch is non-trivial. And that is because from a programmer's standpoint, when you have a lot of different micro tasks that have been separated out from the I/Os that they are waiting on, or that they need to be that they need to get coordinated with, that becomes a challenging algorithmic task for a programmer, because they may have to deal with the fact that these I/Os may complete in a very unpredictable order. But not only that, many times there are dependencies among these micro tasks, and so that requires careful management, including various kinds of synchronization overheads in order to give the illusion of sequential progress of whatever the higher level application algorithm might be. But an even more difficult task for a programmer is handling errors, exceptions, failures in an asynchronous arrangement, where a failure of an I/O, right, might have non-local implications, where some follow-on activity which is supposed to, for example, free up a pointer, does not run, and as a result, some piece of memory now essentially is now a memory leak. There are those kinds of issues, but there are many others, right, that make it generally non-trivial for an average programmer to write I/O reactive code from scratch, especially if it's a very complicated application. So fortunately, we have a very mature framework called NetI in Java, which is available for performing organizing network I/O for applications. And what this particular framework takes advantage of is that it recognizes that most networking applications and their networking interactions are very emblematic of protocols, where whatever the complications of application logic might be, at the point where the I/O needs to be performed and where the results of that I/O need to be shepherded back into the application, at least at that point, the behavior is very much like a state engine, and therefore a mature framework, right, that can provide support for such state engines, which are which essentially are representing data and control flows in applications. Right? If that kind of framework is available, and it's available also for staging computations, providing network services, and for providing whatever buffering in an efficient fashion, then we have a complete solution. Now, this also is benefiting from the fact that many of these low-level network protocols are already in existence, and very often the designer of an application only needs to either use an existing network protocol or extend it in very incremental ways, and that's the another capability that NetI provides. Jordi Gerona from in a talk called NetI from the Trenches, for which we have a link at the end of the presentation, describes NetI very concisely as a tool to implement network applications. Let me just illustrate what this reactor pattern is that NetI and in general the Java frameworks before NetI really capitalize on. So we have a ladder diagram here of different application and I/O components, and then the core part of this is the part in the middle called the event loop reactor. So let's illustrate this with an example. An application issues a request. The request gets forwarded to an event demultiplexer. The event demultiplexer then organizes the asynchronous I/O for that application. And at some point that I/O completes, and the completion gets queued up for the reactor. And then the reactor, imagine that it's going ahead and plugging away at handling these completions. It picks up the next event that it needs to handle. And let's imagine that just requires it to call an application posted event handler, such as a completion or a resolution of a feature or a promise that the application has set up. So that happens, that call finishes, and then the handler is done, and the control is given back to the event loop, and the application, on the other hand, right, is proceeding. in parallel, let's say that the application has issued a second request, then a similar kind of flow proceeds for that second request, and its completion also gets queued up for the reactor, and the reactor picks that up. So you got this parallel execution of the application and the reactor with Netty providing a lot of the support for carrying out these operations in a well organized manner. But now let's just make this probably a little bit more interesting. The reactor in this case, right, calls a handler, but that handler in its execution ends up generating two more synergistic requests from the application. So these are two more new IO requests, right? And they will now follow a life cycle of their own, right? That will continue. So in effect, you've got this activities being propelled in a straightforward fashion in this way. And at some point, let's imagine that the event loop reactor runs out of things to do, then it can yield or poll. But even if it polls, it's not really wasting too many resources because it's a single entity, right? It's the only thing that is polling, and even then, it can potentially sandwich some other activities while it's polling. So that's the reactor pattern. That reactor pattern has been extended into a kind of a twofold reactor pattern called a boss reactor and a worker reactor. And this goes back to the Java frameworks, right, that existed prior to Netty. So what's the idea here? We noticed that when the reactor pulled up a completion and dispatched an application provided handler, that there was perhaps some modest amount of compute involved. What if that modest amount of compute wasn't, or what if that amount of compute was not modest at all, but would impose a significant amount of computational delay? So rather than serializing everything behind the ability of a single thread to perform these things, the more latency sensitive and generally speaking, not computationally intensive pieces may be handled by a boss reactor. It might do high level things like monitor connect events and perform accepts. And then when those accepts occur, it can delegate the accepted connections to sub-reactors. Let me just take a quick time check. Yeah. And then the worker reactor, on the other hand, can perform a lot more computationally intensive things, and it can also be supported on the back of a worker thread pool. So this achieves the same effect that we were having with the single reactor pattern. But now that effect has been generalized to a multi-reactor pattern. So you have these accepted connections on which more computation intensive and more bandwidth intensive tasks may also run. For example, there may be a significant amount of encoding or decoding that may be going on in the course of a send or receive. And what Netty does is it embodies this reactor sub-reactor pattern in its structure, and its goal is to make it very easy to consume from applications, and we'll see how that is achieved. So at a cartoon level, here is the progression that happens. Netty also has a reactor sub-reactor pattern. The requesters might have two-step interactions with a server. So Netty is, by the way, symmetrical. There's a client version of Netty and there's a server version of Netty. They are the same Netty. So you got the connection request coming in, and an event loop that is handling the boss reactor group performs the accepts, and then forwards those things, those accepted connections over to the sub-reactor group. And now the sub-reactor group essentially dedicates some number of threads for each I guess one thread per group of connections. And then that sub-reactor group will do its own event reactive things like responding to reads and writes. And as those events happen on the connection channels, right, the sub-reactor group will invoke its channel handlers and perform those tasks. So the main idea here is that the channel handlers that are shown here, they are reacting to the data that they receive, right? So and they can be chained to create data flow pipelines. So this allows us to think of these pieces as Lego blocks, right? That can be put together and extended as needed. The other thing is that channels are an abstraction that corresponds roughly to endpoints. And event loops are an abstraction that codifies or that embodies control flows. And channel futures are the ones that give us a way to bridge from asynchronous notifications to synchronous interactions based upon things that are waiting for those futures to be resolved. And then the other important thing is that the channels are not demultiplexed among threads. In other words, the I/O traffic for a given connection is always going to be handled by a single worker thread, and therefore that eliminates the need to synchronize among worker threads. Right, so we can handle multiple connections in parallel, but that is done by connection level parallelism rather a higher level parallelism, application level parallelism, rather than connection level parallelism. That was the logical view of how a interaction proceeds through NetE. On the right hand side, we have got a stack view of NetE, and recommend this excellent presentation by Norman Maurer, which goes into much greater details about NetE. Much deeper than what we are doing in this tutorial. So there are the big pieces here are the NetE core, which contains three important pieces: a zero copy byte buff, which is an extension of the or a specialization of the original Java byte buffer network byte buffer implementation. There's a universal communication API that handles very common operations like connection setup and acceptance and so on, reads, writes, exceptions, etc. And there's an extensible event model because the standard event handlers that are provided by NetE can be overridden and extended as necessary. Then we have the support for a variety of different transports. Here we are only showing three, but there's a very rich collection of transports that NetE already incorporates. And there is a very rich set of protocols that NetE supports, from legacy text binary protocols to various kinds of protocols for large file transfers, real-time streams, compression, decompression in the flow, and so on. And then, of course, web level protocols, HTTP, SSL, Google Protobuf, etc. Again, I want to emphasize the point that what Lego is really, what NetE is doing is providing a collection of Lego blocks and making it very easy, almost organized collection of these different pieces into whatever data chaining pipelines that one might want to do. So we'll illustrate that with a simple with a simple toy usage of NetE. So imagine that we have a echo example, and we've taken this echo example from NetE's GitHub page. You have an echo server. It's talking to multiple clients, and each of these clients is sending it a message, and the echo server merely echoes such a message back. How does what does this look like in terms of NetE programming? The easy part to describe is the is the simple flow of the receives and turning those receives back into sends. So the Echo server handler, right, which is the worker, the worker part of the equation here, simply extends a standard construct called channel inbound handler adapter, and it extends it by adding to the channel read an operation called context write, called write, and the write takes into account the context in which this worker is operating. And it may also optionally override a channel read complete in order to go ahead and flush that flush that write. So this it's as simple as writing the entire Echo server, right? It's just basically the heart of its logic is contained in these few lines of code. Then on the left hand side, we have got the bootstrapping where the Echo server right gets set up and gets organized into a part that might accept connections, connection requests, perform the binds, and then on the right hand side, right, invokes or rather plugs in the channel inbound handler adapters. So what is highlighted here is the largely boilerplate code, but what is not highlighted is mostly the boilerplate code. So what is shown here is the key places where one might want to focus when one wants to extend this in any way, customize it in any way. So you might want to, for example, as you're creating the boss group and the worker group, specify the number of threads that you might want to field. And whatever is the server handler, right, that gets defined and simply gets added as a pipeline component to the channel initialization call. When that call is performed, after that setup is completed, right, a channel feature gets set up for performing for receiving the completed operation of a bind, and that essentially binds that server to a socket, and then ultimately later on when that socket gets closed, a closed feature gets resolved, and following that the channel gets closed, and a flushing sink is issued. So this is this is really in a nutshell what Netty looks like. What does the performance look like? So here we are showing a flame graph view of the Echo example. If anybody is not familiar with flame graphs, right, they're a very useful tool to inquire into where time is getting spent. The horizontal axis essentially represents the total amount of time, and the vertical stack represents the nested operations that get performed and that are essentially identified by the profiler as consuming whatever fraction of the time at the higher level, right, or at the bottom level. And what we are seeing here is that on the left hand side of this red line are all of the active operations, right? So this is the place where all the work is getting done. So it's not an issue. We are executing our work. We are mostly spending our time in various kinds of application operations quite fruitfully. On the right hand side, however, we have got an issue. We're spending a chunk of time primarily doing ePOL wait, right? And so this is one of the things where Netty can only take you so far. If you are not taking advantage of the asynchronous services provided by Netty to really perform multiples of these IO requests back to back, so that you don't have to constantly wait in the kernel, then you're going to have to incur this overhead, and this overhead is of two parts, right? Both the waiting overhead as well as the kernel entry exit overheads. Some of that can be eliminated in a fairly straightforward fashion by having the clients perform some amount of batching, so they can, on their side, use netting in order to go ahead and submit multiple requests before they go ahead and harvest the request of whatever, harvest the results of whatever it is that they're waiting for. So that would amortize the waiting, and there would still be the issue of still entering the kernel for the time that is wasted in waiting. So what does one do in order to deal with this? This one can issue concurrent requests at the netty client, as we said, and that certainly raises the relative throughput. We still have to deal with the kernel I/O time and kernel compute time, and we'll get to that. So now we introduce something called IO-U-ring. Very popular framework that has been in Linux kernel, I think at least for the last 3 years plus. It's a great way to achieve concurrency between what's going on in the application and what's going on in the kernel, so that the application kernel essentially are able to queue up things for each other and achieve high levels of efficiency, rather than the application constantly having to go into the kernel all the time. So an application might submit requests to a submit queue, and the kernel, on the other hand, will harvest those submit requests and performs them on behalf of the application. And then the kernel will post its responses or completions back to the application in a separate set of queues or completion event queues, and the application harvests those. So it's a flexible communication channel between application and kernel, just like the reactor pattern was using event queues for decoupling otherwise synchronous interactions. Here also we have a IO-U-ring, which is a dual queue, a submit queue and a completion events queue in order to perform similar decoupling. There's no cross traffic between the submissions part of the channel and the completions part of the channel. Here is a cartoon sketch. From the application side, requests are simply submitted, and they go to the tail of the submission queue. From the kernel side, every once in a while, the kernel will simply harvest multiples of these queued up requests and perform them. As the kernel performs them, it now has its chance to enqueue completions at the tail of a completion queue. And whenever the application finds it convenient, it can harvest those completions. And so this kind of a dual state engine progression can happen on part of the applications in the kernel. Now, there's still the issue of the application having to inform the kernel that it has submitted something for the kernel to do. And there's an option that allows it to do pulled submit, so that the kernel can auto submit on behalf of the application. Now let's just talk very briefly about memory handling IO-U-ring. All of these data structures that we just walked through, the submission queues, the completion queues, and whatever data buffers they refer to, they are all placed in a area of memory that is shared between user and kernel. As a result, there is no need to do any copying through IO-U-ring. And there's also lockless synchronization between user and kernel operations, largely done by performing memory ordering and fencing at the boundaries of these IO operations, or essentially at the boundary of the submit and completion operations. And there is a small detail that on the submit side, there's a level of indirection that is there between the submit queue entries and the submission array slots that the application uses in order to achieve a decoupling from the submission queue entries and whatever memory data buffers at whose lifetime the application may wish to control independently. All of this may sound very complicated, but one of the nice things about IO-U-ring is that there's a library to help application writers with the most natural way of preparing a submission and submitting it, or harvesting a completion and performing the needful cleanup upon completion. So with that, let me invite my colleague Dinesh to take us forward.
Thank you, Joshi, for all that talk there. So just building upon that, what Doshi had laid a foundation here. So there's a lot of material in the IO that available online, but the focus here is more like how we can integrate IO with the NetI. And as we have seen from the previous slides, NetI provide a very rich IO framework for application to build upon that. And so the application can just focus on the business logic itself and not have to worry about networking or all the system level details. So similar concept extend to IO. So here there's an artifact that is available online, and using the IO for NetI is very simple. So all we need to do is compile this artifact in that project file by putting this dependency in there. And once you put this artifact dependency here and compile it, IO is all ready to be used with the NetI. So this is a simple comparison that we put together. How in a NetI-based application can utilize IO in comparison to ePOL or NIO event. So NetI abstract most of the details for the application, and here instead of creating an ePOL event loop, NetI application will generally create an IO event loop group, and everything kind of flows similar after that. So just a couple of line changes and building the artifact in the application project file will get you started with the NetI using the IO and achieve all those goodness for the IO performance, eliminating most of the system calls that can hinder some of the performance for the application here. So it's pretty simple there. And some of the experiment that we did in our lab, here it shows, when we enable the IO with NetI, tail latency can significantly get reduced here. So you can see 99% of percentile latency for the heavy IO can get reduced from almost a microsecond to a couple of hundred millisecond to a couple of hundred microseconds. So it's almost reduced to 1/5 of the tail latency when we are using the IO with the NetI. So moving along from the IO there's another technology that we wanted to just introduce here that can help and high performance network utilization and steering the traffic for multiple applications to a right set of resources there. So if you look at the traditional network deployment in a microservices environment, or when you have many applications talking to many server applications, so you have one NIC pipe that is going across the systems, and then multiple applications is using those same NIC and sharing the same NICs. So all the traffic from client, all the applications, client application get assembled in the same Ethernet wire, and it gets load balanced using some of the technology like receive side scaling or flow sheet tiering, but eventually that does not eliminate dependency of one application to another. So traffic from app one can still create a head of line blocking or some congestion for the another application. So depending upon how much traffic is going from one application, the performance of application two can be impacted in that, because NIC has multiple queues and all those queues still getting load balanced across multiple of those application traffic, and they're all getting steered there. So it can create some sort of congestion or some sort of jitter depending upon what application you are running in the system and how they're behaving it. So sometimes it can create some of this unpredictability because of having those multiple applications sharing the same resources and sharing the same. So this is where the technology that we have in the Intel product application device queue, which can help. So what is device ADQ? So it's not really a protocol, but it's a mechanism where we can identify the application traffic and do the traffic filtering and traffic steering for those applications and direct them to a particular set of queues and a set of resource in there. So here we can have multiple applications. So it's showing like NVMe or TCP, some database or some tiering application. And we can allocate a set of dedicated queues from the global set of pools of queues from the NIC and say, these set of queues are dedicated for that particular application, and only the traffic from that application can go to that particular set of queues. So none of the other applications traffic can be directed to there. So whatever traffic comes for the application, that will be coming to that. So that means, those queues are dedicated to that application, and application is free to utilize it and to how it wanted to use or when it wanted to use and those kind of stuff. So, and depending upon application requirement, you can allocate, one queue, multiple queues, or, so, but those all the traffic belongs to the application will always be directed to those set of queues. And because we have a dedicated set of queues for those applications, so now we can align those application threads to those queues. So further, instead of depending upon interrupts coming on from the NIC, application can use some sort of polling. So whenever application is free, available to do I/O, it can go and get the packets from the queues, respected queues from that, and continue to processing the I/O. So we could eliminate need of interrupts, and from that sense, we can eliminate the context switches that can cause a lot of jitter and a lot of unpredictability in this environment. And that another thing that in the previous slide, you could do this traffic bandwidth limitation on the TX side and that. But yeah, so go ahead on the next slide. So Doshi. So this is showing pictorial version of without ADQ. You have set of queues, and all the traffic from yellow, orange, blue, all sort of traffic from different applications, they can get intermixed in a same lane or same queue in the resource in the NIC, and because of all the mixing happening in there, so you can get a head of line blocking or some unpredictable behavior that can impact your latency or can cause a much higher jitter in that. So when you put the ADQ in that framework, now your traffic is very smooth. So you have all the application traffic from the yellow application will go to the set of queue that are dedicated for the yellow application, and similarly other applications can go to there. And then you have at the bottom you have some default queue, so where which is more like a catch-all thing. So you dedicate some of the queues that are that can still function as in a traditional way. So all the traffic that you don't care of that, or that doesn't have that high SLA requirement, then that can go to those default queues that we have at the bottom. So we have a lot of data available, collateral and data available at that intel.com/ADQ. But this slide, because ADQ is more of a hardware feature or the kernel feature, so it's pretty much transparent, and it seamlessly works with all sort of applications there. So it works with bare metal application, JVM, containerized, virtualized, or the NATI application that has been the the talk of this presentation or focus of this presentation. So it all works, transparently for those applications. So, but we have a lot of, collateral that shows NetE can help improve performance for cache tiering applications, for the databases applications or the storage applications. So, and it reduce, jitter and improve the latency to more than 60-70% of the tail latency. It can help improve there. So there's a lot of resources. There's a lot of performance data available at intel.com/ADQ that's there. But yeah, so this slide, all our presentation and the slide that talks about additional resources that we can go about NetE, about IO ring, about ADQ. So there's a lot of presentations we have in that. So there's a link and YouTube presentation that we can refer to. But I think this is probably our last slide, right? Yeah, so the summary, I'll go over, summarize some of those talks that we have done, modern high performance system design. They require asynchronous IO processing to effectively utilize system resources, CPU storage as this, all high CPU system available. Then you need the asynchronous IO. NetE provide a protocol agnostic, asynchronous and event-driven network framework that application can utilize it and build upon that, and it abstract most of that IO framework that is required for the networking programmability, and the application can focus on the business logic and not to worry about all those nitty-gritty details of that programming in that. But as we've seen that from the flame graphs, from that some of the presentation, that the highly chatty nature of the microservices environment can still, create a lot of system calls and activity with the operating system, and that can impact the system performance greatly, and it can increase the latency because of the context switches that come from switching from the user space to the kernel space and going back and forth. And so IO ring technology that can help minimize those system calls and the context switches, because application and the kernel, they function in their domain and doesn't have to make the system calls. And as we've seen this from the previous, IO ring performance data, that can help greatly reduce the context switches and can improve the tail latency for that environment by reducing the system IO call. ADQ, application device queue, further can help in the traffic filtering based on the applications, and allowing that application to meet their SLAs by steering that to the dedicated set of queues and dedicated set of resources, and doing this traffic limiting on the transmit side. You could put that limits on how much traffic can an application can use, or bandwidth application can use. So all sort of the details that application can allow and maintain that SLA, that predictability or SLA that you need for an application, and it can be enabled for the JVM application or NetE application. So it can help improve throughput and the latency from that perspective.
So David, we are, I think we are at the end of our presentation. If there are any questions we can answer.
Yes, virtual round of applause. Thank you very much. That's a great coverage of NetE and other really interesting technologies like IO ring and ADQ. I'm not seeing any questions in the chat, but if anyone has any, by all means, please unmute and ask away. I think we have about 10 minutes on the schedule. One question I have, maybe it's, a lot of this is new to me, so maybe I'm off with a question like this, but with NetEase's reactor pattern, it seems really interesting. First of all, I assume it's kind of general, right? Not specific to NetEase. It seems like a general design pattern. Is that correct?
Yes, absolutely. It's a design pattern that shows over and over. It shows up over and over.
Yeah, that makes sense. Seems like a great one. Especially because it seems like great at handling lots of I/O, assuring event queues are handled asynchronously and such. What I'm wondering is, if things go wrong, is it difficult to debug? Because it seems like a very sophisticated runtime. However, if the underlying, say, NetEase runtime is very robust, maybe it's not a problem at all. Is there anything you could say about that?
Yeah, I can say a couple of things. One is that it's a very mature framework with very, very wide adoption. So it
Nice.
does get a significant amount of pounding and testing. But the other thing too is that because of the way that it basically encapsulates a lot of what is already standard and allows you to extend. Typically, your debugging responsibilities, right, are really part of your application and your application logic, and that's where the modern constructs like futures and other things that which actually formalize this. No, I want to wait for something, but I don't necessarily want to have a thread switch. I just want to have a task switch, which is task or whatever you want to call it, function switch. Right? I want to have the ability to pick up the next work that I have to do and carry it forward. And I don't necessarily have to give up the CPU right now. So that obviously is something that requires some degree of maturity in programming, and that can give rise to its own bugs. And I think standard practices should apply. But at least as far as having some challenges with respect to bugs kind of creeping up from the IO part of the stack into application part of the stack and causing undesirable effects, right, and making it difficult. And I think NetEase to a large extent, and even the way that the IO Uring is structured, right, remove those issues.
That makes sense. That's great to hear. Let's see, anything else? Any other questions? Well, we have a moment. I'll just remind folks that the Hot Interconnects committee has created a poll just so we understand where folks are coming from, how they're hearing about the conference, and we'd like to grow. So if you could please take a moment to just participate in a poll we have. It took me less than 5 seconds. You just say whether or not you're from LinkedIn or industry or other. That would be very helpful for us. Any other questions or thoughts?
If I may just add one more thing overall, right? Is that what we have done here is draw from really rich resources that other people have created, right? Norman Maurer for NetEase, Jens Axbo for IO Uring. Right, so most of the credit for the material really goes to them. We have just packaged it in a way that would fit within a 50-minute format.
Yeah, I was thinking the same thing. You sort of packaged things nicely together and made that connection between these really interesting tools, I guess you would call them. Well, unless there are any last minute questions, I think we can wrap it up. Thank you so much.
I think people are hungry.
I'm certainly hungry myself. Yeah. And it'll be a short lunch, right? Which is half an hour, and then we'll get right back to it with some SmartNIC discussion. So about half an hour from now, 30 minutes plus 5 or so, we will start back up with a long tutorial on SmartNICs. And then I think also lunch begins in track 1. And the final talk of the day there will be on OFI libfabric. So we hope to see you there.
Thank you.
Thanks, Doshi, Dinesh, and team. That's great. Appreciate it.